Hello students, in this lecture we will discuss the basic concepts of engineering thermodynamics. Now we will discuss the derivation of air standard efficiency of Otto cycle, diesel cycle and dual cycle. There are two types of cycles when we discuss Otto cycle, diesel cycle and dual cycle. One is thermodynamic cycle and another is mechanical cycle. Mechanical cycle is basically composed of suction stroke, compression stroke, expansion stroke and exhaust stroke. Means mechanical cycle includes the processes in which there is movement of piston. Whereas thermodynamical cycle starts from the initiation of compression. So thermodynamical cycle consists of compression process, heat addition process, expansion process and heat rejection process. It does not involve suction and exhaust. Suction and exhaust are part of mechanical cycle, whereas heat addition and heat rejection are not involved in mechanical cycle. One thing more, from the starting of compression, that is from point 1, that is compression process, heat addition process, expansion process, heat rejection process and again to the point 1. A constant mass of working substance is there inside the cylinder. So this process or these processes can be modeled as a control mass system, that is a closed system, so that the non-flow work can be calculated as PDV, integration of PDV, because that makes our analysis simpler. And as the system has been modeled as closed system, therefore the energy calculation can be done easily by the first law, that is with the help of equation del Q is equal to du plus del W. So basically from the point 1 to the point 1 again, that is involving process 1, 2, 3, 4, 1, the system can be modeled as closed system, and this is basically the thermodynamic cycle. If we want to discuss all the processes that are covered in mechanical as well as thermodynamic cycle, so let us begin. 0 to 1 is suction taking place at constant pressure. Then 1 to 2, it is reversible adiabatic compression, and I have told you in the engineering thermodynamics syllabus subject that the process which is reversible and adiabatic is isentropic. So I think you are able to recall this. Then heat addition is taking place at constant volume, means combustion has initiated. Then followed by that is reversible adiabatic, that is isentropic expansion, during which we get power and pressure starts decreasing. Then heat rejection is taking place at constant volume, and from 1 to 0 it is the exhaust process. So the products of combustion or exhaust gases are thrown out of the cylinder. But mind it, the suction and exhaust processes are not shown on the thermodynamic cycle. Now you can draw TS diagram for these processes. As you know that isentropic processes can be shown by vertical lines. So 1 and 2, 3 and 4 processes, that is 1 and 2, 3 and 4, they are the isentropic processes and they have been shown by the vertical line. Whereas constant volume processes are shown by inclined curve on the TS diagram having slope with the positive x-axis. Now, when we are deriving the expression for air standard efficiency, let me tell you that as the working substance is air only, instead of fuel plus air plus residual gases, several parameters like Cp, Cv, gamma, R, they are assumed to be constant throughout the range of operation. Range of operation means the temperature varies from 300 Kelvin to 2000 or 2500 Kelvin or so, or even higher, depending upon the compression ratio of the engine and many other factors. And the pressure is varying from almost 1 bar or even slightly lower to 70 or 80 bar or higher, depending upon the capacity of engine and compression ratio and many other factors. So you can see the range of operation, 1 bar to 70 or 80 bar, or you can say temperature 300 Kelvin to 2000 Kelvin or 2500 Kelvin. So even then, these parameters Cp, Cv, gamma, R are assumed to be constant. So that is the assumption, mainly to simplify our evaluation of efficiency. Moreover, it is also assumed that there is no disintegration of the working substance throughout the range of operation. So all these assumptions are basically to simplify our assessment of efficiency. There is one more term, mean effective pressure, whose derivation we are going to discuss just after air standard efficiency. Mean effective pressure is nothing but it is the constant mean effective pressure that is acting on the piston of a hypothetical engine that is producing power equivalent or equal to an actual engine. As you know that in the case of actual engine, the pressure varies and it varies drastically. Means if we take the example of 4-stroke engine, let me tell you the pressure is varying from 1 bar or even lower than to 70 or 80 bar, because in the 4-stroke engine all the processes will take place in the 2 revolutions of the crankshaft, or you can say 720 degree of crank travel. So the pressure is varying, say, from 1 bar to 80 bar, and then during expansion stroke it again reduces and it further reduces during the exhaust stroke. So first of all, we take up the assessment of air standard efficiency. For this we assume unit mass of an ideal gas in a piston cylinder arrangement which is undergoing all the 4 processes of thermodynamic cycle. Now for the unit mass of an ideal gas, the heat supplied at constant volume will be equal to Cv dt, that is T3 minus T2. Why so? Because we have assumed it to be a closed system, so definitely del Q is equal to du plus del W is going to be our energy equation. And when volume is constant during heat addition process, it means work done will be 0, PdV work will be 0. So heat transfer is equal to change in internal energy, and that is equal to Cv dt. So Cv into T3 minus T2 is the heat added. Similarly, heat rejection takes place at constant volume. So heat QL is equal to Cv into T4 minus T1. Thermal efficiency is equal to work done upon heat supplied, or you can say uh, work done can be made equal to heat supplied minus heat rejected. So what we get, 1 minus heat rejected upon heat supplied. So our expression becomes, that is shown in equation 3. As we take T1 common in the numerator and T2 common from the denominator, our expression becomes as shown in equation number 4. Now we discuss all the processes one by one. Process 1 to 2 is adiabatic compression. So the relation between temperature and volume is T2 upon T1 is equal to V1 upon V2 raised to power gamma minus 1, that is equal to R raised to power gamma minus 1, where R is compression ratio. As I have told you earlier, R is equal to V1 upon V2, that is compression ratio. Similarly, the relation between the pressure and volume is equal to P2 upon P1 is equal to V1 upon V2 raised to power gamma, that is equal to R raised to power gamma, shown by equation. There is one more parameter which is alpha, and that is pressure ratio. So that is alpha is equal to P3 upon P2, and that is also equal to T3 upon T2 because volume is constant. So gas law is applicable. P into V upon T is equal to constant. That is what we have applied over here. Process 3 to 4 is adiabatic expansion. So P3 upon P4, that is equal to V4 upon V3 raised to power gamma. So now, as you know, that from 4 to 1 volume is constant, so V4 is equal to V1, and volume is constant also from 2 to 3, that is heat addition process. So V3 is equal to V2. So that expression becomes V1 upon V2 raised to power gamma, that is equal to R raised to power gamma. Similarly, T3 upon T4 is also equal to V4 upon V3 raised to power gamma minus 1, and which is also equal to V1 upon V2 raised to power gamma minus 1. So it becomes T3 upon T4 is equal to R raised to power gamma minus 1. Now, as heat rejection is taking place at constant volume, V4 is equal to V1. So from the equation 5 and 7 we get T2 upon T1 is equal to T3 upon T4. By cross multiplication we can infer that T4 upon T1 is equal to T3 upon T2. Substituting these values in equation 5 of 5 and 8 in equation 4, the expression for air standard efficiency yield us 1 minus 1 upon R raised to power gamma minus 1. So basically the expression of air standard efficiency is depending upon the compression ratio. If we want to find out P4 upon P2, so that can be written as P4 upon P3 into P3 upon P2, that is equal to 1 upon R raised to power gamma into alpha. Now if we want to find out mean effective pressure is nothing but it is basically work done upon swept volume, because we know that mean effective pressure is as work done upon swept volume. From where this expression is coming? That is quite simple. Work done is equal to PdV. So P is equal to work done upon dV, that is swept volume. Now first of all we want to find out work done. So work done is nothing but the area enclosed by geometrical entity or geometrical figure of the cycle on PV diagram, that is net cycle diagram area, that is representing the work. So here if we see this diagram, the area bounded by curve 1, 2, 3, 4, 1. Within this curve, that is representing its work. So what we are going to do, the area under the curve 3, 4 minus the area enclosed by the curve under the curve 1, 2, that is going to give you the area within the enclosed diagram or enclosed figure, that is 1, 2, 3, 4, 1. So that has been represented by equation number 11, that is P3 V3 minus P4 V4 upon gamma minus 1 minus P2 V2 minus P1 V1 upon gamma minus 1. Now what we do, dividing both numerator and denominator by P2 V2, we get work done is equal to the P2 V2 into alpha minus 1 into R raised to power gamma minus 1 upon gamma minus 1 into R raised to power gamma minus 1, the expression shown in 12. What we have done basically over here, we have reduced the entire expression for work done in terms of pressure, volume, alpha, gamma and R. And these pressure terms also we will reduce in the terms of P1 V1. And finally we will be having the expression in the terms of P1, that is initial pressure, alpha, R and gamma. That is what we are going to do. Now we know swept volume is equal to V1 minus V2. Because V1 upon V2 is equal to R, so we have written RV2 minus V2. So our expression becomes what has been shown in equation number 13. Now as I told you, MEP, mean effective pressure, is equal to work done upon swept volume. So the expression becomes as shown in equation number 14. As I have told you earlier, in the terms of P1, that is initial pressure, R, alpha, gamma. So all the students are required to work out these derivations for air standard efficiency and mean effective pressure. If they get any of this, they can ask me. They can write their problems through mail. Now this is diesel cycle. Diesel cycle is basically having heat addition at constant pressure. All the other processes are similar to that in Otto cycle. And one more difference that lies between diesel cycle and Otto cycle is that diesel cycle is having higher compression ratio than an Otto cycle. So the thermodynamic cycle begins from point 1. So reversible adiabatic isentropic compression of the working substance is taking place. Then heat addition takes place at constant pressure. Then reversible adiabatic, or that is isentropic expansion of the working substance is taking place. Then heat rejection at constant volume. Similarly, all the processes have been shown on TS diagram. So isentropic processes will be shown by vertical lines, whereas constant pressure and constant volume, both curves will be inclined curves. The difference lies in that constant volume curve is having more slope than constant pressure curve on. Now similar type of exercise we are going to do for the evaluation of air standard efficiency and mean effective pressure for a diesel cycle. In the diesel cycle, heat addition is taking place at constant pressure. So for the unit mass of an ideal gas, heat supplied is equal to Cp into T3 minus T2. Why heat transfer is equal to CpTT for an ideal gas during constant pressure process? That we are going to discuss in our unit 3 dealing with the Maxwell relations. Now for the constant volume heat rejection, the amount of heat rejected is Cv dt, that is Cv T4 minus T1. Thermal efficiency, which is equal to 1 minus QL upon QH, is shown by the equation 3. Now dividing numerator and denominator by Cv, what we get is shown on the slide. Now dividing numerator and denominator by T1, we get the expression as shown in equation number 4. Now we discuss all the processes one by one. For adiabatic compression process, the relation between the temperature and volume is shown, and what we get is T2 upon T1 is equal to R raised to power gamma minus 1. This is similar as we have done in the case of Otto cycle. And P2 upon P1 is equal to R raised to power gamma, where R is compression ratio. Heat addition is taking place at constant pressure, and there is we introduce a new term which is known as cutoff ratio, which is an important parameter in the determination of air standard efficiency of diesel cycle. And this cutoff ratio is nothing but ratio of the volume after heat addition and before heat addition. So V3 upon V2, and that is also equal to T3 upon T2 because pressure remains constant. Process 3 to 4 is reversible adiabatic expansion. So P3 upon P4 is equal to V4 upon V3 raised to power gamma, and since V4 is equal to V1 and V3 is equal to rho times V2 as given in the equation number 6, we finally get the expression as R upon rho raised to power gamma. Similarly, T3 upon T4 becomes R upon rho raised to power gamma minus 1. Heat rejection is taking place at constant volume, so V4 is equal to. Now we express all the temperature ratios in equation 4 in terms of R, rho and gamma. So T2 upon T1 is equal to R raised to power gamma minus 1 as we have expressed earlier. T3 upon T2 is equal to rho that we have also expressed earlier. Now T4 upon T1, that can be written as T4 upon T3 into T3 upon T2 into T upon T1. So that becomes equal to rho raised to power gamma as shown in the equation 8. So you can work out this. Now the expression for air standard efficiency is equal to 1 minus rho raised to power gamma minus 1 upon gamma R raised to power gamma minus 1 into rho minus 1. So you can see cutoff ratio is playing an important role apart from the compression ratio in the expression for air standard cycle. Now for the work done, because we want to find out mean effective pressure, and that can be done by the formula work done divided by swept volume gives mean effective pressure. So the area within this geometrical diagram we have to find out. So that is equal to P2 into V3 minus V2, the area of the rectangle, plus area under the curve 3, 4 minus the area under the curve 1 to 2. That is going to give you the area within the enclosed diagram 1, 2, 3, 4, 1. So that is equal to P2 into V3 minus V2 plus P3 V3 minus P4 V4 upon gamma minus 1 minus P2 V2 minus P1 V1 upon gamma minus 1. So now similar type of exercise we are going to do. We divide both numerator and denominator by P2 V2 and we try to get this expression in terms of P1 rho gamma. Swept volume we have expressed in the similar way as we did in earlier in the case of Otto cycle, and finally we get the expression for MEP in the terms of P1 R gamma and rho. This is dual cycle on which high speed diesel engines operate. So the process 1 to 2 is reversible adiabatic, that is isentropic compression of working substance. Then heat addition takes place at constant volume. followed by the heat addition at constant pressure. Then reversible adiabatic or isentropic expansion of the working substance is taking place, and finally heat is rejected at constant volume. So all the processes have been shown on the TS diagram. The isentropic processes have been shown by the vertical lines, whereas constant pressure and constant volume curves have been shown by inclined curves. So constant volume curve is having more slope than constant pressure process. That is evident on the TS diagram. Now for the unit mass of an ideal gas, heat supplied is equal to Cv into T3 minus T2 plus Cp into T4 minus T3, because heat addition is taking place partly at constant volume and partly at constant pressure. Heat rejected is equal to Cv dt, that is Cv into T5 minus T1. So the thermal efficiency, which is equal to 1 minus QL upon QH, becomes as what is shown in equation number 3. Dividing numerator and denominator first by Cv and then by T1, we get the expression as shown in equation number 4. So we are having different temperature ratios in the equation number 4. So now what we have to do? We have to find out the values of these temperature ratios. So we describe all the processes one by one. Adiabatic compression, similar to the previous both cases, we are having T2 upon T1 is equal to R raised to power gamma minus 1 and P2 upon P1 is equal to R raised to power gamma. Now process 2 to 3, heat addition is taking place at constant volume. We define here the term alpha pressure ratio as we did in the case of Otto cycle. So that is equal to P3 upon P2 and that is also equal to T3 upon T2. Process 3 to 4, heat addition is taking place at constant pressure. Here we define the term cutoff ratio as we did in the case of diesel cycle. So that cutoff ratio is equal to V4 upon V3 and that is equal to T4 upon T3. 4 to 5 is adiabatic expansion process. So P4 upon P5 is equal to V5 upon V4 raised to power gamma. Since 5 to 1 is constant volume process, so V5 is equal to V1 and V4 can be written as rho times V2. So P4 upon P5 is equal to R upon rho raised to power gamma, and similarly T4 upon T5 is also equal to R upon rho raised to power gamma minus 1. Also P5 upon P2 is equal to P5 upon P4 into P4 upon P3 into P3 upon P2. So that becomes rho upon R raised to power gamma minus 1 into alpha. Now expressing all the temperature ratios in equation 4 in terms of R, alpha, gamma and rho, what we get is T2 upon T1 is equal to R raised to power gamma minus 1, T3 upon T1 is equal to alpha into R raised to power gamma minus 1, T4 upon T1 becomes rho into alpha into R raised to power gamma minus 1, and T5 upon T1 becomes equal to alpha into R raised to power gamma. So this is nothing but simplification, simple mathematics. Substituting the values of equation 5, 9, 10 and 11 in equation 4, what we get is, we get the expression of air standard efficiency in terms of R, gamma, alpha and rho as shown in the equation number 12. Now here also what we are going to do to determine the expression for mean effective pressure for dual cycle, we want to find out the work done. That is, we want to find out the area enclosed by this geometrical figure, that is 1, 2, 3, 4, 5, 1. So that will be equal to the area of the rectangle, that is P3 into V4 minus V3 plus area under the curve 4 to 5 minus the area under the curve 1 to 2. So that is P3 into V4 minus V3 plus P4 V4 minus P5 V5 upon gamma minus 1 minus P2 V2 minus P1 V1 upon gamma minus 1. Dividing both numerator and denominator by P2 V2, we get the expression of work done as shown in the slide. So what we have to do, we have to derive the entire terms for the expression of mean effective pressure in terms of P1, R, alpha, rho and gamma. So this is what we have finally achieved over here. We have achieved the expression for mean effective pressure in terms of P1, R, rho, gamma, alpha. So this is. Now we want to discuss the important terms associated with the IC engine. Top dead center and bottom dead center are the terms that need to be discussed first of all. Top dead center and bottom dead center, as they are abbreviated as TDC and BDC, they are the extreme positions to which piston travel during any of the stroke. Top dead center is defined as the extreme position to which piston travels during compression stroke and exhaust stroke, whereas the bottom dead center is the extreme position to which piston travels during suction stroke and expansion stroke. In the case of vertical cylinder, these centers are defined as top dead center and bottom dead center, whereas in the case of horizontal engine, they are defined as inner dead center and outer dead center. The linear distance between TDC and BDC is known as stroke length. These centers are known as dead centers because they do not move, they are stationary. The inner diameter of the cylinder is known as bore. The cross-sectional area of the cylinder when multiplied with the stroke length gives us swept volume or stroke volume. So the piston travels from top dead center to bottom dead center or bottom dead center to top dead center during any of the stroke. Now the volume remains beyond that is defined as clearance volume. So clearance volume is nothing but it is the volume to which the charge, that is air fuel mixture or air, that is confined at the end of compression stroke. There is one more term which is known as compression ratio. Compression ratio is the ratio of two volumes, that is volume at the beginning of compression stroke and the volume after the or at the end of compression stroke. So if we say that compression ratio of the engine is 6, it means the volume of the charge or air fuel mixture, it is reduced to 1/6 of the volume that was at the beginning of the compression. Another term, cubic capacity or engine capacity, is nothing but it is the total swept volume of all the cylinders of an engine taken together. This is cross section of spark ignition engine. Cylinder block and crankcase are the two structural units of an engine. They are either built separately and then connected together, or they are built integrally. Cylinder block houses all the cylinders of an engine, whereas crankshaft lies in the crankcase. Because it houses the crankshaft, that is why it is known as crankcase. But it also houses several other auxiliary devices like lubricating oil pump, water timing gears, and many more auxiliary devices. In the case of spark ignition engine, air and fuel mixture is prepared with the help of carburetor in a requisite ratio, which is inducted in the cylinder during the suction stroke. Now during the compression stroke, this air fuel mixture is being compressed, and at the end of compression stroke, spark is generated with the help of spark plug mechanism, which initiates the combustion. Slowly the combustion propagates and it produces high pressure gases, which propels the crankshaft of the engine and produces power. Then the products of combustion or exhaust gases are scavenged out of the engine through exhaust manifold. Manifold is nothing but complex pipes are known as manifold. So through inlet manifold, air fuel mixture rushes into the cylinder, whereas exhaust manifold facilitates the scavenging of the products of combustion or exhaust gases. Piston reciprocates inside the cylinder, and the piston is connected to the small end of connecting rod with the help of gudgeon pin or piston pin, and the big end of the connecting rod is mounted on the crankshaft. Connecting rod is having somewhat angular motion. Now we will discuss the working of 4-stroke SI engine. In a 4-stroke cycle engine, the cycle of operation is completed in 4 strokes of the piston, or say 2 revolutions of the crankshaft. Each stroke consists of 180 degree of the crankshaft rotation, and hence a cycle consists of 720 degree of crankshaft rotation. Now the series of operation of ideal 4-stroke SI engine includes 4 strokes, that is suction stroke, compression stroke, expansion or power stroke, and the fourth one is exhaust stroke. Suction stroke starts when the piston is at top dead center and about to move downwards. The inlet valve is open at this time and the exhaust valve is closed. Due to the suction created by the motion of the piston towards bottom dead center, the charge consisting of fresh air mixed with the fuel is drawn into the cylinder. At the end of suction stroke, the inlet valve closes. Compression stroke. The fresh charge taken into the cylinder during suction stroke is compressed by the return stroke of the piston. During this stroke, both inlet and exhaust valve remain closed. The air which occupied the whole cylinder volume is now compressed into clearance volume. Just before the end of the compression stroke, the mixture is ignited with the help of an electric spark between the electrodes of the spark plug located in the combustion chamber valve. Burning takes place when the piston is almost at top dead center. During the burning process, the chemical energy of the fuel is converted into the sensible energy, producing a temperature rise of about say 2000 degrees Celsius, and the pressure is also considerably increased. Expansion or power stroke. Due to high pressure, the burnt gases force the piston towards bottom dead center, both inlet and exhaust valve remaining closed. Thus, power is obtained during this stroke, and both pressure and temperature decrease during expansion. Exhaust stroke. At the end of expansion stroke, the exhaust valve opens, the inlet valve remaining closed, and the piston is moving from bottom dead center to top dead center, sweeping out the burnt gases from the cylinder. The exhaust valve closes at the end of exhaust stroke and some residual gases remain in the cylinder. Each cylinder of a 4-stroke engine completes these 4 operations, that is suction, compression, expansion and exhaust, in 2 engine revolution. 1 revolution of the crankshaft occurs during the suction and compression strokes, and the second revolution during the power and exhaust strokes. Thus, for 1 complete cycle, there is only 1 power stroke while the crankshaft turns by 2 revolutions. Now we'll discuss the working of two-stroke engines. In the diagram we have shown the two-stroke SI engine. In two-stroke engines the cycle is completed in two strokes, that is one revolution of the crankshaft as against two revolutions of four-stroke cycle. The difference between two-stroke and four-stroke engines is in the method of filling the cylinder with the fresh charge and removing the burnt gases from the cylinder. In a four-stroke engine, the operations are performed by the engine piston during the suction and exhaust stroke, respectively. In a two-stroke engine, suction is accomplished by air compressed in crankcase or by a blower. The induction of compressed air removes the products of combustion through exhaust ports. Therefore, no piston strokes are required for suction and exhaust operations. Only two piston strokes are required to complete the cycle, one for compressing the fresh charge and the other for expansion or power stroke. The charge is sucked through spring-loaded inlet valve when the pressure in the crankcase reduces due to upward motion of the piston during compression stroke. After the compression, ignition and expansion takes place in the usual way. During the expansion stroke, the air in the crankcase is compressed. Near the end of the expansion stroke, piston uncovers the exhaust ports and the cylinder pressure drops to atmospheric as the combustion products leave the cylinder. Further motion of the piston uncovers transfer ports, permitting the slightly compressed air or mixture in the crankcase to enter the engine cylinder. The top of the piston sometimes has a projection to deflect the fresh air to seep up to the top of the cylinder before flowing to the exhaust ports. This serves the double purpose of scavenging the upper part of the cylinder of combustion products and preventing the fresh charge from flowing directly to the exhaust ports. The same objective can be achieved without piston deflector by proper shaping of the transfer port. During the upward motion of the piston from bottom dead center, the transfer ports and then the exhaust ports close and the compression of charge begins and the cycle is repeated. Now we compare SI engine and CI engine. If we see basic cycle, SI engine works on Otto cycle, or you can say constant volume heat addition cycle, whereas CI engine works on diesel cycle or constant pressure heat addition cycle. As far as fuel is concerned, SI engine operates on gasoline, which is a highly volatile fuel, and the self-ignition temperature of this fuel is quite high. CI engine is operated with diesel oil, which is a relatively non-volatile fuel. Self-ignition temperature is comparatively low. So here self-ignition takes place in the case of CI engine as the temperature is quite low. Introduction of fuel. In the case of SI engine, a gaseous mixture of fuel air is introduced during the suction stroke. Carburetor, which is preparing the air fuel mixture, is supplying the mixture in requisite ratio, and the ignition system, which is igniting the mixture, are the requisite components of the system. But modern engines are having gasoline injection system. In the case of CI engine, what is happening? Air is basically compressed during the compression stroke and fuel is injected directly into the combustion chamber at high pressure at the end of compression stroke theoretically. So for this function, a fuel pump and injector are necessary. Now in the case of SI engine, as the load is varying, it is the throttle that is controlling the quantity of fuel air mixture according to the load. Whereas in the CI engine, as the load is varying, the quantity of fuel is regulated. Air quantity remains almost constant. In the case of SI engine, we are having a ignition system which is having spark plug in the combustion chamber. So primary voltage is provided either by a battery or by a magneto to produce the requisite spark at the electrodes. In the case of CI engine, self-ignition occurs due to high temperature of air because of the high compression. So ignition system and spark plug are not necessary. Now the compression ratio of SI engine is having the value ranging from 6 to 10. Why we not go beyond 10 or a particular value? Because knocking starts. As the compression ratio increases beyond a certain limit, knocking starts. So upper limit is basically fixed by anti-knock quality of the fuel. If we increase the anti-knock quality of the fuel, it means if we are using a fuel which is having better anti-knock quality, definitely it will be expensive one, but we can raise compression ratio. But again, there is a trade-off between the economics of the fuel and the anti-knock quality of the fuel. The compression ratio of CI engine is varying from 16 to 20. But in the present times, we are having the vehicles in which the compression ratio have increased even beyond 24. Means it is somewhat like 24.5 or so. Why we not go beyond the higher limit? That is, why don't we go for 25, 26, 27 and 28 compression ratio in the case of CI engine? Here it is not limited by the knocking as it was in the case of SI engine. But basically, as the compression ratio increases, the value of P2, that is pressure of the compressed air, will rise, and definitely it is going to increase the weight of the engine, because to sustain that high pressure, definitely cylinder and other parts have to be strong enough, which will increase its weight, and ultimately it is increasing the overall weight of the engine. In the case of SI engine, due to lightweight and also due to homogeneous combustion, high speed is allowable, whereas in the case of CI engine, due to heavy weight and also due to heterogeneous combustion, we can allow only low speed operation. Because of lower CR, the maximum value of the thermal efficiency is lower in the case of SI engine, but because we are having a good value of compression ratio in case of CI engine, the maximum value of thermal efficiency is higher. As we have discussed in previous lecture, the derivation of the air standard efficiency, you can very well recall that air standard efficiency depends upon compression ratio, whether it is SI engine or CI engine. Weight of SI engine is lighter due to lower peak pressures, whereas CI engines are heavier due to high peak pressures. Now, before going for the discussion for the comparison of 2-stroke and 4-stroke engines, I'd like to discuss general expression for power, which is equal to PM into A into L into N divided by small n. So PM is basically referring to mean effective pressure, A is referring to area of piston, L is referring to length of stroke, capital N is referring to rotational speed of the engine in revolution per second, and small n is referring for number of revolutions required to complete the one engine cycle. If it is two-stroke engine, then n is equal to 1. If it is four-stroke engine, then n is equal to 2. In the four-stroke engines, the thermodynamic cycle is completed in 4 strokes of the piston or in 2 revolutions of the crankshaft. So, 1 power stroke is obtained in every 2 revolutions of the crankshaft. Whereas in the two-stroke engine, the thermodynamic cycle is completed in 2 strokes of the piston or in 1 revolution of the crankshaft. Thus, 1 power stroke is obtained in each revolution of the crankshaft. In the four-stroke engines, because of the above fact, turning movement is not so uniform. So to make that uniform, we need heavier flywheel. And in the case of two-stroke engine, turning movement is more uniform. So lighter flywheel will be sufficient. In the case of four-stroke engines, because of 1 power stroke for 2 revolution, power produced for the same size of engine is less, and for the same power the engine is heavier and bulkier. This can be explained by the expression that I have shown you on the previous slide. Here we were having the expression Pm into L into A into N upon small n. So basically in the case of four-stroke engine, that small n is equal to 2. So it means power produced for the same size of the engine, means if we are having same value of Pm, same value of stroke length, same value of cross-sectional area of piston, and same speed of the engine, then definitely in the case of four-stroke engine, the power produced will be half that produced by the two-stroke engine. And if we want to make both the engines of same power, that is two-stroke and four-stroke engine, then definitely we will have to compensate the factor of 2. To compensate for the factor of 2, definitely we will have to increase either of the parameters, that is either Pm or L or A or capital N, that is speed. But remember, Pm, that is mean effective pressure, and capital N, that is speed of the engine, that cannot be increased. That is not in our control. So what can be increased? A into L, that is cross-section area and stroke length. It means ultimately we are increasing the size of the engine if we want to keep the power of four-stroke engine to be the same as that for two-stroke engine. For two-stroke engine, because of 1 power stroke for every revolution, power produced for the same size of the engine is twice, or for the same power the engine is lighter and more compact. Because of 1 power stroke in 2 revolutions, lesser cooling and lubrication requirement is there. So rate of wear and tear is lower. In the case of two-stroke engine, because of 1 power stroke in every revolution, the cooling requirement and lubrication requirement is higher. So higher rate of wear and tear is there. In four-stroke engines have valve and valve actuating mechanism for opening and closing of valves. In the case of two-stroke engine, there is no valve, but only ports are there. Because of comparatively higher weight and complicated valve mechanism, the initial cost of engine is more. In the case of two-stroke engine, because of the lightweight and simplicity due to absence of valve actuating mechanism, initial cost of the engine is less. In the case of four-stroke engine, volumetric efficiency is more due to more time of induction. Because what we are having the entire operation to be carried out in 720 degree of crank travel, whereas in the case of two-stroke engine, volumetric efficiency is low due to lesser time of induction, because here all the processes are to be covered up in just one revolution, that is 360 degree of crank travel. Thermal efficiency is higher for 4-stroke engines, whereas thermal efficiency is lower in the case of 2-stroke engine. 4-stroke engines are used where efficiency is important, in cars, buses, trucks, tractors, industrial engines, aeroplanes, power generation. 2-stroke engines are used where low cost, compactness and lightweight are important, that is in mopeds, scooters, motorcycles, hand sprays, etc., and in lean engines. The figure shows the energy flow through the reciprocating engine. According to the first law of thermodynamics, energy can neither be created nor destroyed. It can only be converted from one form to another. Therefore, there must be an energy balance of inputs and outputs. In the reciprocating internal combustion engine, fuel is fed in the combustion chamber where it burns in the air, converting its chemical energy into heat. The whole of this energy cannot be utilized for driving the piston, as there are losses to the exhaust, to the coolant and to radiation. The remaining energy converted to power is called the indicated power. This is utilized to drive the piston. The energy applied to the piston passes through the connecting rod to the crankshaft. In this transmission, there are energy losses due to friction, pumping, etc. The sum of all these losses converted to power is termed as friction power. The remaining energy is the useful mechanical energy, which is termed as brake power. In energy balance generally, friction horsepower or friction power is not shown separately because ultimately this energy is also lost through exhaust, cooling water and radiation. What basically brake power is? Brake power is the power developed by the engine at the output shaft. So that can be calculated by the formula tau into omega, which can be simplified as 2 pi nt. So T is basically torque in Newton meter and N is the rotational speed in revolution per second. And how the torque can be calculated? Torque can be calculated by the multiplication of force at the dynamometer and the radius arm. So we can calculate the brake power easily. The total power developed by the combustion of fuel in the combustion chamber is, however, more than the brake power and is called indicated power. Out of the power developed by the engine, that is indicated power, some is consumed in overcoming friction between moving parts, some in the process of inducting the air and exhausting the products of combustion from the engine combustion chamber. Indicated power is the power developed in the cylinder and thus forms the basis of evaluation of combustion efficiency or the heat release in the cylinder. The difference between the indicated power and the brake power is the indication of power lost in the mechanical components of the engine. Indicated thermal efficiency basically indicates the ratio of the integrated power to the energy produced by the burning of fuel. Whereas brake thermal efficiency defines the ratio of brake power to the energy produced by the burning of fuel. The mechanical efficiency is defined as the ratio of brake power to the indicated. Volumetric efficiency of an engine is an indication of the measure of the degree to which the engine fills its swept volume. It is defined as the ratio of the mass of air inducted into the engine cylinder during the suction stroke to the mass of the air corresponding to the swept volume of the engine at atmospheric pressure and temperature. Alternatively, it can be defined as the ratio of the actual volume inhaled during suction stroke measured at the intake condition to the swept volume of the piston. The volumetric efficiency of the engine puts a limit on the amount of fuel which can be efficiently burned in an engine because the power output is proportional to the amount of air inducted. Mean effective pressure is basically hypothetical pressure which is thought to be acting on the piston throughout the stroke that results in the same amount of indicated or brake work produced by the engine. Thus, one can see that for a given engine, the power output can be measured in terms of mean effective pressure. If the mean effective pressure is based on the BP, it is called as brake mean effective pressure, and if the mean effective pressure is based on indicated power, it is known as indicated mean effective pressure. Specific fuel consumption is defined as the amount of fuel consumed per unit of power developed per hour. It is a clear indication of the efficiency with which the engine develops power from the fuel. So specific fuel consumption is fuel consumed in grams per hour per unit power in kilowatt. So brake specific fuel consumption is determined on the basis of brake output of the engine, while indicated specific fuel consumption is determined on the basis of indicated output of the engine. This parameter is widely used to compare the performance of different engines. Okay, for this lecture, we will continue our discussion pertaining to the concepts of thermodynamics in our subsequent lectures. Till then, bye.